Everything you've been told about how the sun will kill the Earth is wrong. Not slightly wrong, catastrophically, embarrassingly wrong. And the real story? It's so much worse than an explosion. I want you to imagine standing on Earth 5 billion years from now. The sky isn't dark. It's red. It's enormous. And it's not exploding, it's swallowing. The horizon, you know, the comfortable blue dome that has been above every human who has ever lived, is gone. Replaced by something ancient and enormous and indifferent. And the strange part? That image is the optimistic version of what's coming. Because by the time the sun looks like that, the story for life on Earth will have ended long before the sky turns red. But let's not start there. Let's start with right now. And look, I almost said, when the sun explodes, just then, which tells you exactly how deeply this misconception is baked into all of us. Even making this documentary, I had to stop myself 3 times from using that word. Explode. It's the wrong word entirely. And by the end of this, you'll understand why, and you'll be able to explain the actual story to anyone, at a dinner table, in under 2 minutes, and watch their expression change. That shift in someone's face when a thing they've assumed their whole life turns out to be wrong. That's what we're here for. 3 specific things I want you to hold on to as we go. First, the phase that's already started, right now, today, as you're watching this. Second, the moment Earth actually becomes uninhabitable, and why it's not billions of years away in the way you've been led to believe. Third, why the sun's quiet death is, in some measurable physical sense, more violent than any supernova we've ever recorded elsewhere in the universe, and why you will never, ever see it happen. We're going to travel 8 billion years into the future and come back with a different understanding of right now. Let's go. The sun is not the stable, eternal lamp we assume it to be. It is a slowly brightening, slowly dying star, and both of those facts, taken together, are catastrophic for us. Here's what the sun actually is at its core: a fusion reactor. Every single second, it converts roughly 600 million tons of hydrogen into helium. To put that in terms of something you can picture, that is the entire mass of Mount Everest, fused every 30 minutes. It has been doing this for 4.6 billion years. It has another approximately 5 billion years of hydrogen fuel left. So in terms of its main fuel supply, the sun is at about the halfway point. But here's why halfway is deeply misleading. The second half of the sun's life looks nothing like the first half. A car that's halfway through a road trip is still a car. The sun halfway through its life is already changing shape, changing temperature, changing everything. It is not the same sun it was when Earth formed. Right now, the sun is approximately 30% brighter than it was 4.6 billion years ago. 30%. That is not a rounding error. That is a fundamentally different star. In fact, early Earth survived the young sun only because the atmosphere at that time was thick with carbon dioxide, creating a natural greenhouse effect strong enough to compensate for the dimmer star. Scientists called this the faint young sun paradox. For decades, it took genuine effort to explain why Earth wasn't a frozen ball of ice 4 billion years ago. The answer, when they found it, was clarifying and terrifying in equal measure. Earth's habitability has always been on a knife's edge. It was engineered by atmospheric chemistry to compensate for a dim sun. And now, as the sun brightens, that same atmospheric chemistry will eventually stop being able to compensate in the other direction. The sun's luminosity increases by roughly 1% every 110 million years. That sounds slow, and it is, by human standards. But we've been through 46 of those cycles since the sun lit up. The brightening is not coming. It is ongoing. You are living inside it. To understand where this is going, picture the Hertzsprung-Russell diagram, the graph astronomers use to classify stars by temperature and luminosity. Our sun is currently on what's called the main sequence, a stable band where stars spend most of their lives burning hydrogen. But the sun is not sitting still on that diagram. It is drifting toward the upper right, toward the red giant branch, and it has been drifting since the day it was born. The engine of all this change is something called the helium accumulation problem. As the sun fuses hydrogen into helium, the helium ash piles up in the core. This ash doesn't participate in fusion, it just sits there, pressing down, making the core contract under its own weight. The contraction heats the surrounding layers, which causes them to expand outward. The sun gets brighter. The outer layers grow. Slowly, but relentlessly, the sun is reorganizing itself from the inside out. Here's something I couldn't shake while thinking about this: the helium in birthday balloons. There's a version of this story where some of those atoms were synthesized in ancient stars that died billions of years before our sun was born, scattered across the galaxy as stellar exhaust, eventually swept up when our solar system formed. You're celebrating with dead stars' byproducts. Make of that what you will. So the sun is brightening. It has been brightening for 4.6 billion years. But here's what nobody tells you: the timeline for when that becomes our problem is not measured in billions. It's measured in hundreds of millions. And the clock? It started ticking long before humans existed. Venus is not just a hot planet. Venus is a preview. It is what happens when a planet loses its battle against a brightening sun, and Earth is on the exact same trajectory, just running on a later schedule. Venus and Earth are nearly identical twins by any cosmic measure. Same size, same mass, same basic composition, formed in the same neighborhood of the early solar system. Yet Venus has a surface temperature of 465 degrees Celsius, hot enough to melt lead, hot enough to incinerate a spacecraft within minutes of landing, hot enough to kill any chemistry we associate with life. This is not a quirk. This is the most important data point in this entire documentary. Current scientific consensus, based on climate modeling work published by Michael Way and colleagues at NASA JIS in 2019, suggests Venus was likely habitable for somewhere between 2 and 3 billion years. It probably had a shallow ocean. It probably had a stable climate. And approximately 700 million years ago, something tipped it over an edge it couldn't come back from. What ended it was a cascade, a combination of solar brightening, volcanic outgassing, and what scientists call a runaway greenhouse effect. And runaway is exactly the right word. A small temperature increase causes water to evaporate. Water vapor traps heat. More heat causes more evaporation. More evaporation traps more heat. The feedback loop has no natural break. It accelerates until there is no water left, and a world that once looked like Earth now looks like the inside of a furnace. Earth's current position, $1 from the sun, keeps us just outside the theoretical runaway greenhouse limit. But as the sun brightens, that limit moves outward. The boundary expands. And eventually, within roughly 600 million to 1.5 billion years depending on which climate model you consult, the runaway greenhouse limit crosses Earth's orbit. Venus's atmosphere today is 96% carbon dioxide. The atmospheric pressure at the surface is 90 times Earth's, the equivalent of being 900 meters underwater. This is not a random planetary accident. It is the thermodynamic end state of what happens when a water world loses its oceans. The water didn't evaporate and stay in the atmosphere, it was destroyed. Hydrogen, the lightest element, escapes to space. Oxygen bonds with surface rocks and disappears from the atmosphere. Over millions of years, Venus's entire ocean was dismantled atom by atom and scattered to the cosmos. The universe doesn't give second chances. It just moves on. ESA and NASA are both currently planning missions to Venus specifically to investigate its ancient habitability, the Da Vinci and Envision programs. The questions being asked right now, in active scientific programs, are: was Venus the first habitable planet in this solar system? Did it ever have life? The answers, if we find them, will reshape everything we think we know about the prevalence of life in the universe. Because if Venus had life, and Venus lost it to the same process that is slowly moving toward Earth, then the question of how common habitable planets are becomes much darker. The Sun is not exceptional. There are hundreds of billions of stars like it in our galaxy alone. All of them are brightening. All of them have planets in their habitable zones. And all of those planets are on borrowed time. Venus shows us the end state. The question becomes, how does Earth get there? What are the actual stages? Which phase do we survive, and which one finally ends us? The Sun's evolution follows a precise, scientifically mapped sequence of 5 phases. Each phase represents a different kind of catastrophe. And this is the structural backbone of everything else we're going to discuss, so let's walk through all 5, with actual numbers attached to each one. Phase 1 is where we are right now. The main sequence, hydrogen burning in the core, slow brightening, stable enough from year to year that it feels eternal. We have approximately 5 billion years left in this phase. This sounds like plenty of time. It is not. Because the trouble starts long before phase 1 ends. Phase 2 is the subgiant phase, beginning roughly 5 billion years from now when the core's hydrogen is exhausted. The core contracts, the surrounding hydrogen shell ignites, and luminosity spikes dramatically. This phase is critically underappreciated in popular discussions. Most people jump from the Sun today straight to red giant. But the subgiant phase is where the Sun becomes dangerous to inner planets long before it visibly looks much different. The suffering, to borrow a dramatic frame, comes before the spectacle. Phase 3 is the red giant phase, peaking approximately 7.5 billion years from now. The Sun expands to roughly 200 times its current radius. Mercury is incinerated. Venus is swallowed. Whether Earth is consumed, and this is a genuinely unsettled scientific question, depends on a gravitational race we'll examine in detail shortly. Phase 4 is the helium flash and the horizontal branch. When helium in the core reaches approximately 100 million Kelvin, it ignites in a runaway thermonuclear event, releasing as much energy in a matter of minutes as the Sun normally emits in 100 million years. Then a temporary stabilization as helium fusion settles into a new equilibrium. The Sun contracts slightly, burns helium for about another 100 million years. A brief, strange interlude before the final act. Phase 5 is the asymptotic giant branch, followed by the Planetary nebula and the white dwarf. A second expansion, larger and more violent than the first. Then the outer layers are shed entirely, forming an expanding shell of glowing gas, the Planetary nebula. What remains is the compressed core, a white dwarf, roughly Earth-sized, radiating stored heat into space for trillions of years. No explosion. No drama visible from another star system. A quiet dimming. I want to stop at that white dwarf image for a moment, because it genuinely affected me when I first sat with it. The entire sun, compressed down to the size of Earth. Still glowing. Alone. With no planets. No life anywhere nearby. Just radiating heat into empty space until it fades. There's something almost melancholy about that. The universe is full of things that become tragic if you think about them long enough. Anyway, let's keep going. Scientists have identified a specific threshold, a crossing point where Earth's fate is sealed, not by fire from space, but by the very star that created life here. That threshold is closer than any extinction event in Earth's past. And we are heading toward it at the same speed every day. Earth doesn't become uninhabitable when the sun becomes a red giant 7 billion years from now. It becomes uninhabitable approximately 600 million to 1 billion years from now, and the mechanism is not heat. It's starvation. Let me explain the silicate carbonate cycle, because this is the most important and least known piece of the whole story. Earth has a geological thermostat. When temperatures rise, chemical weathering of rocks accelerates. Rocks react with CO2 in rainwater, pulling carbon dioxide out of the atmosphere and locking it in mineral form. Over geological time, this keeps CO2 levels and temperatures from spiraling out of control. It's the reason Earth hasn't become Venus already. But here's the trap: as the sun brightens, temperatures rise, weathering accelerates, and CO2 gets pulled out of the atmosphere faster than volcanoes can replenish it. The thermostat, which was Earth's salvation for 4 billion years, becomes Earth's executioner. CO2 levels drop. And they drop below a threshold that matters enormously for life. C3 photosynthesis, the process used by wheat, rice, most trees, most of the plants that support every terrestrial food chain, fails below approximately 150 parts per million of CO2. The current atmospheric concentration is around 420 parts per million. Caldera and Casting calculated in 1992, and multiple research groups have since refined the number, that C3 photosynthesis ends approximately 600 million years from now. Not from heat. From CO2 starvation. Most plants die. Food chains collapse. Complex animal life ends. C4 plants, corn, sugarcane, certain grasses, can survive lower concentrations, down to roughly 10 parts per million. They buy another 200 million years. But complex animal life requiring dense, layered ecosystems doesn't have those 200 million years. The window for beings like us closes around 600 to 800 million years from now. Beyond 1 billion years, surface temperatures rise enough to begin significant ocean evaporation. As water vapor rises into the stratosphere, the same Venus process begins. UV radiation dismantles water molecules, hydrogen escapes to space, oxygen bonds with iron in the crust. Complete ocean loss, estimated between 1.1 and 1.5 billion years from now. After that, Earth is a dry, hot, geologically dead rock. Scientists model two possible pathways from here: the moist greenhouse, where Earth loses its water slowly over hundreds of millions of years, and the runaway greenhouse, where it accelerates catastrophically in the Venus manner. Current models slightly favor the moist greenhouse for Earth, but the destination is identical either way. No water. No life. No recovery. Here's where the comparison to past extinction events becomes important. The Permian-Triassic extinction, the Great Dying, 252 million years ago, killed roughly 96% of marine species and 70% of terrestrial vertebrates. It was the worst catastrophe life on Earth has ever faced. And life recovered. Within 10 million years, ecosystems were rebuilding. The solar brightening event is categorically different. It doesn't kill life and allow recovery. It terminates the conditions that allow life to exist. It's not an extinction. It's a closing. There's a way of looking at this that I find genuinely strange to sit with. If intelligent life had evolved on Earth 600 million years earlier, which is within the realm of biological possibility, they would be having this exact conversation right now, looking at a deadline already in their past. They would be gone. We exist in a window. And all windows close. Now, here's where the story takes a turn I didn't expect when I started researching this. Because while all of this is happening to Earth over the next billion years, there's a specific sequence of events happening to the Sun itself that is, in some ways, even stranger. The Sun's death isn't a single event. It's a transformation. And one of those transformation stages produces a phenomenon we have never directly observed, because no instrument built by human hands has ever captured it live. The helium flash is one of the most physically violent events in stellar physics. It is entirely invisible from outside the star. It is the Sun's most dramatic moment, and no one will ever see it happen. Here's the setup. When hydrogen in the Sun's core is finally exhausted approximately 5 billion years from now, the core contracts under gravity and heats up. A shell of hydrogen just outside the core continues burning, feeding energy into the expanding outer layers. The helium core keeps contracting, keeps heating, until it reaches approximately 100 million Kelvin, the ignition temperature for helium fusion. But here's where the physics becomes remarkable. In normal stellar gas, when temperature rises, the gas expands, pressure drops, and the fusion rate self-regulates, a negative feedback loop that keeps stars stable. In the Sun's helium core at this point, however, the electrons have been squeezed into what physicists call a degenerate state. Degenerate matter doesn't follow normal gas laws. Pressure in a degenerate gas doesn't depend on temperature. So when helium ignition starts and heat is produced, the pressure doesn't increase, the gas doesn't expand, the fusion doesn't slow down. More heat means more fusion means more heat, a runaway reaction with no natural break. The helium flash releases approximately 10 to the power of 43 joules of energy in a matter of minutes. To put that in perspective, that is roughly equivalent to the entire luminosity of the Milky Way galaxy sustained for a few seconds. The most energetic event our Sun will ever experience. And none of it reaches the surface. The overlying layers of stellar gas absorb all of it. From Earth's theoretical future perspective, if any observer existed, the Sun might flicker almost imperceptibly. Maybe dim slightly as energy is absorbed. Then resume expanding as before. The most violent thing the Sun has ever done, and it presents itself as a hiccup. The degeneracy is lifted by the flash itself, the helium fusion stabilizes, and the Sun settles into the horizontal branch, a temporary equilibrium burning helium in the core for another 100 million years. We have never observed a helium flash in real time. Our entire understanding comes from stellar evolution models, astroseismology, and observations of star populations in clusters, comparing stars before and after the flash by studying many stars at different evolutionary stages simultaneously. It is one of the most rigorously confident predictions in all of astrophysics. And yet no human instrument has ever watched it happen. What the triple alpha process produces during helium fusion is carbon. Free helium, 4 atoms fuse into one carbon, 12 atom. Every carbon atom in every carbon-based life form on Earth was built through this process, either in the Sun's future, or in ancient stars that died billions of years before the Sun was born. The helium flash is the origin of organic chemistry in the universe. The reason biology is possible at all. The fact that the single most energetically powerful event our sun will ever experience, an event happening inside our own star, will be completely invisible, there's something philosophically significant about that. The universe's most important moments aren't always the loudest ones. Sometimes the most consequential things happen in silence. After the helium flash, the sun expands again, this time into the asymptotic giant branch, the final red giant phase before the sun sheds its outer layers entirely. And this brings us to a question that is genuinely, actively unsettled in planetary science: will Earth be physically swallowed? Whether Earth is consumed by the expanding sun is one of the most compelling open questions in our field of study, and the answer depends on a race between two forces playing out over millions of years. Here are the competing forces. On one side, orbital migration. As the sun loses mass during the red giant phase, shedding roughly 30% of its total mass via stellar wind, its gravitational pull on Earth weakens. Earth's orbital radius responds by expanding outward. The math here is clean: orbital radius scales inversely with central mass. Earth's orbit could migrate from its current $1 to somewhere between 1.3 and $1.50 by the time the sun reaches peak red giant size. On the other side, tidal drag. The enormous distended sun exerts a gravitational bulge effect on Earth's orbit, pulling Earth slightly inward with each orbital pass, like a slow braking force. This is the same mechanism the Moon uses to gradually slow Earth's rotation, operating in the opposite direction. The most detailed calculation we have, published by Schroeder and Smith in 2008, the paper most frequently cited in this specific debate, concludes that Earth will likely be engulfed, but only barely. Tidal drag wins the race by a slim margin. Earth spirals inward and is vaporized approximately 7.59 billion years from now. However, this conclusion is model-dependent, and other research groups, using different mass loss rate assumptions, reach different conclusions. The Earth survives scenario is not fringe. If the sun loses mass slightly faster than Schroeder and Smith assumed, Earth's outward migration exceeds tidal drag. Earth survives as a scorched, airless, waterless, geologically dead rock, orbiting a sun that has now expanded and partially retreated into a white dwarf configuration. Habitable? Absolutely not. Physically intact? Possibly yes. Whether survival in that form counts as survival is a question for philosophers, not astronomers. There's also a mechanism called ram pressure to consider during the final engulfment phase, if it occurs. As a planet orbits within the envelope of an expanded star, it experiences drag from the stellar plasma. This is distinct from tidal braking and may actually dominate in the final inward spiral. Papers addressing this specific problem were still being published in the early 2020s. The physics here is genuinely cutting edge. We also have observational evidence, from white dwarf spectra, that rocky planetary material does fall into dying stars. White dwarfs across the galaxy show pollution, heavy elements in their spectra that shouldn't be present if rocky debris hadn't been accreted after the stellar death. The engulfment scenario isn't purely theoretical. We see its aftermath, frozen in light, across thousands of light years. What engulfment actually means, if it happens to Earth, is worth describing clearly, not a dramatic impact or explosion. Earth would orbit within the sun's outer layers, plasma thin enough to allow orbiting but dense enough to cause rapid orbital decay. Earth spirals inward over thousands of years, gradually ablating from the outside in, until the compressed remnant reaches the solar core and merges. A process drawn out over millennia. Undramatic in any single moment. Inevitable in aggregate. I kept thinking about this while going through the Schroeder and Smith paper, that the question of whether Earth survives is genuinely unsettled. Some of the sharpest minds in planetary science have spent careers on this specific problem and cannot give a definitive answer. There's something I find almost comforting in that. Not every question has been answered. The universe still has secrets. Some of them are about our own home. After the red giant phase, whether or not Earth survives it, the solar system is unrecognizable. The sun has shed its outer layers. What remains is tiny, intensely hot, and slowing down. And in the process of dying, the sun creates something extraordinary. This is the part I want you to really sit with. After the asymptotic giant branch, the second, final red giant expansion, the sun's outer layers are expelled in a series of pulsations. Not in an explosion. In a series of slow, magnificent exhalations. These expanding shells of gas, illuminated by the intense ultraviolet radiation from the newly exposed core, form what astronomers call a planetary nebula. It glows for approximately 10,000 years before dispersing into the interstellar medium. And it is one of the most beautiful structures in the known universe, swirling rings of ionized oxygen, nitrogen, carbon, and hydrogen, in colors that cameras can capture but human eyes were never designed to process unaided. Here is the revelation that changes everything. A planetary nebula from a sun-like star contains carbon, nitrogen, oxygen, and trace heavy elements synthesized across billions of years of stellar fusion. These elements don't disappear. They join the interstellar medium, the raw material from which the next generation of stars and planets forms. The sun's death seeds the galaxy with the chemistry of life. There is strong evidence that our own solar system's formation was triggered partly by the expanding nebula of a nearby dying star, a pressure wave compressing a cloud of interstellar gas until gravity took over and the sun ignited. The sun may have been born from the death of another star. And its own death will provide the raw material for future stars. A cycle operating across billions of years, with each generation of stars building on the elemental legacy of the last. What remains after the nebula disperses is the white dwarf, the sun's compressed core, approximately Earth-sized, initially glowing at surface temperatures exceeding 100,000 Kelvin. No fusion. No fuel. Just stored thermal energy radiating outward into space, cooling at an almost incomprehensibly slow rate. A white dwarf takes approximately 10 to the power of 15 years to cool to a black dwarf, a quadrillion years. The current age of the universe is 13.8 billion years. The universe is not old enough for a single black dwarf to exist yet. Every white dwarf ever formed, in the entire history of the cosmos, is still glowing somewhere. And here is the moment that rewrites the emotional arc of this entire documentary, the thing that made me stop working and just sit for a while. White dwarfs, as they cool, undergo a phase transition. Their carbon and oxygen interiors, under extraordinary pressure, crystallize. The core of the cooling sun becomes, structurally, an enormous diamond. We have confirmed this observationally. The white dwarf BPM 37093, nicknamed Lucy, located 50 light-years away, was confirmed in 2004 via astroseismology to have a crystallized core. The measurement from Travis Metcalfe and colleagues, a single crystal of carbon approximately 10 to the power of 34 carats. The largest diamond ever identified by science. Our sun, approximately 5 billion years after it becomes a white dwarf, will crystallize. The sun, the star that ignited life on Earth, that drove every photosynthetic reaction in 4.5 billion years of evolutionary history, that set the rhythm of every day in every organism that has ever lived, ends as a diamond. Cooling in the dark. Alone. Still carrying, in its crystalline structure, the compressed memory of everything it ever was. But not gone. Never truly gone. Because everything it made, every carbon atom in your body, every oxygen molecule and every breath you've ever taken, these atoms came from stars that died exactly this way. The sun's death is not an ending. It is the sun's most significant contribution to the universe. When I first understood this, not just as facts but as a story, I had to stop working for a while. Because it completely changed how I think about the star above us. I used to look at the sun as background, as ambient, as just there. Now I look at it and think, that thing is alive. It has a story, a beginning, a middle, and an end. And we are a tiny, temporary, extraordinary part of its middle. That stopped feeling depressing somewhere in the writing of this. It started feeling like something worth knowing. So we know what the sun will do. The question becomes, is there anything we can do about it? And the answer, which sounds like science fiction but is not, is possibly yes. The key proposal was published in 2001 by Koryansky, Laughlin, and Adams, under the title Astronomical Engineering, a Strategy for Modifying Planetary Orbits. The concept, by repeatedly directing large asteroids or Kuiper belt objects past Earth on precisely calculated trajectories, their gravitational pull transfers tiny increments of kinetic energy to Earth's orbit, shifting it outward, incrementally, over millions of years. The required orbital migration is approximately 0.3 to 0 Australian dollars and 50 cents outward over roughly 500 million years, to keep Earth within the habitable zone as the sun brightens past the CO2 starvation threshold. The required flyby frequency, approximately one close pass of a 100-kilometer diameter asteroid every 6,000 years. Over a million years, that's around 160 flybys. Over 500 million years, roughly 80,000. Demanding, but not physically impossible. The energy source for the whole operation is the sun's own gravitational field, accessed through the orbital energy of the redirected bodies. The risks are sobering. The margin for trajectory error is extraordinarily small. Koryansky and colleagues calculated roughly a 1 in 15 chance of catastrophic Earth impact per flyby if trajectories deviate even slightly from optimal. Engineering at this precision, sustained over millions of years, requires not just technology we don't yet have, it requires civilizational continuity across timescales that dwarf all of recorded human history. Every institution we currently have, every government, every civilization, has existed for thousands of years at most. This program would need to run for hundreds of millions. Alternative proposals include deploying large solar radiation reflectors at Earth's L1 Lagrange point to generate a gentle outward push via radiation pressure. Less risk of catastrophic failure, but requiring even longer sustained maintenance. The move to Mars consideration is worth raising separately. As Earth becomes uninhabitable over the coming billion years, Mars, currently too cold and atmosphere thin for complex life, would move into a warmer orbital band and become potentially habitable during the red giant phase. For a limited window. Colonizing Mars doesn't save Earth, but it extends the timeline for life in this solar system by potentially hundreds of millions of years. I want to be straightforward about the timescales here. We have approximately 600 million years before the CO2 starvation becomes critical. That is 600 million years. For context, the entire history of complex animal life on Earth, every fish, every dinosaur, every mammal, every human civilization, spans approximately 600 million years. We have one full history of animal life worth of time to figure this out. Humanity has existed for roughly 300,000 years. We are at the very beginning of the time available to us. The question isn't whether we have enough time. The question is whether we choose to use it. But all of this assumes something important, that we survive long enough to attempt any of it. Because before we worry about the sun in 600 million years, there are solar threats operating on human timescales, threats measured in decades, not eons. And we are, at this moment, substantially unprepared for them. On the first 2 days of September, 1859, the sun had one of its worst days in recorded history. A coronal mass ejection, a billion-ton bubble of magnetized plasma, struck Earth's magnetic field directly. The result was the Carrington event, the most powerful geomagnetic storm in the instrumental record. Telegraph operators across North America and Europe received electrical shocks from their equipment. Papers caught fire on telegraph desks without being connected to any power source. The aurora was visible as far south as Cuba, Hawaii, and Colombia. Some observers thought their cities were on fire. The National Academy of Sciences estimated in 2008 that a Carrington equivalent event today would cause between $1 and $2 trillion in initial damage in the United States alone, with recovery times of 4 to 10 years, and that estimate is now widely considered conservative, given how much more dependent on electronics our infrastructure has become since 2008. We are currently in solar cycle 25, which as of 2024 and 2025 is tracking notably above initial predictions for activity. The solar maximum of this cycle arrived around 2025, and multiple significant X-class flares have already occurred during this window. The sun is not behaving quietly at this particular moment. It is paying attention to us, in the manner of something that doesn't know we exist but could still end our civilization on a bad Tuesday. The Miyake events make the Carrington event look manageable by comparison. In the years 774 to 775 AD and again in 993 to 994 AD, carbon-14 spikes preserved in tree rings from sites worldwide indicate solar proton events somewhere between 10 and 100 times more powerful than Carrington. These events have no fully satisfying explanation. They arrived without warning, or rather, without any warning system that existed at the time. If a Miyake-scale event occurred today, the concern extends beyond electrical infrastructure to the ozone layer itself, stratospheric chemistry disruptions potentially causing mass extinction-level UV exposure at ground level globally. The 2012 near-miss is the data point that keeps solar physicists up at night. On July 23, 2012, a Carrington-class coronal mass ejection was launched from the Sun. It missed Earth by approximately 9 days. Earth was at a different position in its orbit when the plasma cloud crossed our orbital path. The Stereo A spacecraft measured it directly. Daniel Baker and colleagues published the analysis in 2013, concluding that had this ejection occurred a week and a half earlier, the consequences for modern civilization would have been severe and global. We didn't do anything right. We got lucky. Most national power grids are not hardened against large coronal mass ejections. The most vulnerable and hardest to replace components are large transformers, the infrastructure that steps voltage up and down for long-distance transmission. Manufacturing lead times under normal conditions run 12 to 18 months per unit. Legislation and hardening programs exist in several countries, including the United States and United Kingdom, but implementation remains incomplete relative to the documented risk level. Here's what I find striking about the asymmetry of attention we give these threats. We spend billions modeling asteroid impacts, which are rare, localized, and slow developing, while being structurally unprepared for a solar event that has already happened within recorded human history and is statistically guaranteed to happen again. I'm not dismissing asteroid defense. But the sun is right there. It tells us every 11 years how active it's planning to be. And we keep, mostly, looking somewhere else. We've traveled from right now to 8 billion years in the future, and back. From CO2 starvation 600 million years out, to the helium flash happening invisibly in the sun's core, to a diamond cooling alone in the dark where the solar system used to be. And I want to end not with fear, and not with false comfort, but with the thing I kept coming back to every time I sat down to work on this. Understanding the full arc of the sun's life and death doesn't diminish the meaning of existence. It amplifies it. Consider what the sun's timeline tells us about the Fermi paradox, the mystery of why we don't see intelligent civilizations everywhere we look in the universe, given how many stars and planets exist. One answer: habitable windows are genuinely narrow. A billion-year window sounds vast until you recognize that it represents roughly 7% of a universe's current age, and complex life requires nearly all of it to develop. Intelligence on Earth took 4.5 billion years to appear. We arrive with barely enough time to have this conversation. We may not be common. We may be extraordinarily rare. Astronauts who see Earth from orbit describe something called the overview effect, a permanent perceptual shift where the fragility and beauty of the planet become viscerally, undeniably real in a way that no description prepares you for. Understanding the sun's life cycle produces an equivalent shift, not in space but in time. The conditions for life on Earth right now, the right temperature, the right CO2 range, liquid water, an active magnetic shield, a stable and reasonably quiet star, are the product of 4.5 billion years of interlocking contingencies, all of them temporary. Climate change viewed through this lens looks different. Not, will Earth survive? Earth will exist as a rock for billions of years regardless of what we do. The question is, what kind of Earth do we maintain for the window we actually have? We are not fighting for Earth's existence. We are managing the quality of a window that the sun will eventually close on its own schedule. That reframe matters. It relocates the urgency from existential to practical. The case for becoming a multiplanetary species is also reframed by the sun's timeline. This isn't ambition or adventure, it's the same biological logic that has driven every successful species across evolutionary history. Diversify your habitat range or accept the consequences of concentrated vulnerability. The sun is going to brighten. Earth's habitable window is going to close. At some point, the only way life from this planet continues is if some of it is somewhere else. That is not pessimism. It is arithmetic. And then there's the simplest thing, the value of the present moment, which becomes harder to take for granted once you've genuinely absorbed this timeline. 600 million years from now, complex life on Earth is over. That means everything, every conversation, every discovery, every moment of beauty or connection or understanding, is happening inside a finite window that will one day close without drama, without warning visible to those inside it, just a slow dimming of conditions that once allowed something extraordinary to exist. That is not depressing. That is what precious means. I'll be straightforward with you. When I started this documentary, I thought it was going to be about stellar physics and billion-year timelines. And it is. But making it changed something for me. Because I kept arriving at the same thought, the sun is going to die. Before it does, it will end everything that depends on it. And knowing that, really knowing it, not just filing it away as an astronomy fact, made me look differently at things I usually treat as permanent. The specific color of light at 7 a.m. through a particular window. The way the sky looks between day and night. The fact that all of it was arranged, billions of years ago, by processes that began with a dying star I will never see. That felt important to say out loud. We started this documentary with the claim that everything you knew about how the sun would kill the Earth was wrong. And hopefully now you see why that matters. Because the real story isn't a violent explosion. It's a slow, inevitable, and strangely beautiful transformation. The sun won't go out with a bang. It will go out with a diamond. And long after the last trace of Earth has been absorbed or scattered, the universe will carry the sun's carbon, its oxygen, the atoms forged across 5 billion years of fusion. In future stars. In future planets. Possibly in future life, life that will never know us, but will be built, in part, from what we are made of. Everything is on a cycle. Everything contributes. Even endings. Oh, and one correction before we close. I mentioned earlier that some of the helium in your birthday balloons might have been fused in the sun and traveled to Earth in solar wind. That was me getting carried away with the poetry of the thing. Most terrestrial helium is actually from radioactive decay of uranium and thorium in Earth's crust, alpha particles captured in underground rock formations over billions of years. Not the sun's exhaust. I overclaimed because the science was so compelling. I wanted everything to be connected. Most of it is. Just not that specific part. The sun's story is extraordinary enough without me inventing extra connections. If this changed how you think about the star above us, even slightly, the next documentary is about Jupiter, specifically what Jupiter has been doing to the inner solar system for 4.5 billion years, and why some planetary scientists believe that without Jupiter, Earth would have faced extinction-level impacts once every million years instead of once every 100 million. Jupiter is a significant part of the reason complex life was able to reach the point of making documentaries about the sun dying. That video is already in production. And given what you now know about how rare and temporary habitable windows are, I'd suggest not waiting too long to watch it.